Welcome to the seminar search for directors and almost. Today we have to Dr. Jan. He's a postdoctoral researcher in high energy physics based at CERN. He works on data analysis of for electroweak physics measurements, developing a novel calibration technique to measure the mass of the W boson. He is a physics convener of the Higgs study group as part of the feasibility study for the Future Circular Collider project. He leads the zero operation computed unit of 3 to 4 people responsible for the large-scale data storage and reconstruction, and he supervises students involved in data analysis projects. So welcome, Dr. Jan, and please go ahead.
Thank you for the introduction. The intro slide is not clear, but yes, so I will talk about the recent measurement of the W mass of the CMS experiment. So just a quick introduction. So the idea of doing precision measurement is to try to understand the standard model, but also to try to break the standard model, because we know that the standard model holds strong, but it's not a complete picture of the universe. So in the LHC, we don't have direct evidence of geophysics. And we don't know what will happen with LHC. So a way to form the model is to do precision measurement. So exactly, so after the Higgs discovery in 2012, so the standard model electroweak sector is basically over-constrained. So when we got the Higgs mass, we can do direct measurements of each parameter in the standard model, and then we can allow to probe the consistency of the standard model from the cell. And any deviation that you can find, this you can interpret as new physics beyond the standard model. So it's important that the LHC continues doing this. So the LHC will continue with a lot of data, and then we'll continue doing precision measurements with LHC. So in particular for the W boson mass, so this is the picture before we had the result out in September this year. So for the W boson mass, you can compute the W boson mass based with this equation, which involves W boson mass, Z mass, the Fermi constant, and then some relative corrections. So assuming that you know all these parameters, you can calculate the W mass, and you can do that with all the parameters you have in the BDG, and you have this value with an uncertainty of 6. So the idea of all the standard model analysis for W boson mass is to measure the W boson mass with this kind of precision and see if it matches or not. So we were not the only one, of course, that measured W mass, and it's quite challenging to do. So W mass was discovered at UA1, UA2, at CERN, and also lab Tevatron experiments, and also Atlas and LHCb, where before was measuring the W boson mass. So this is what you can see here, and you can see, of course, this CDF is not in 2022, the latest one from the Tevatron. They show here a value which is very off the average values of all the other measurements, and with a very small uncertainty. So this is 7 sigma away from all the other experiments. So clearly this was a big puzzle in physics in the past years. And so this has to be answered. And also you see here that CMS is not in the list. So we took the message quite seriously, and we tried to measure the W boson mass with a similar precision as CDF and see how that fits in this picture. So how we do the measurement of W boson mass at Hadron Collider? So we do it at Hadron Collider at the LHC. So basically you need to rely on the leptonic decays of the W, because if you do the measurement with the hadronic decays, that's too complicated because of the pilot and etc. So you have to produce your W in hadronic interactions, and then it decays leptonically. So you have the lepton here, electron or muon, and then you have the neutrinos here as well. So how we can measure the W mass from this? So we can measure precisely the electron of the muon. We can also measure, not less precisely, we can measure the neutrino. And then if you plot here, for example, the lepton PT of the muon or the of transverse mass, and here you can see how they look like and how a 10 MeV shift in the W boson mass translates to this shape difference. And what is important to notice here is the scale of the ratio. This is 10 to the minus 3, so it's per mil level that you need to control the distribution. And that's, of course, the challenge of the analysis. So in particular for CMS, what we did is we used part of 2016 dataset corresponding to 16 of 18% market. In that dataset, we have, so it's quite large statistics. We have 100 million selected W bosons, W2 menu. And the average pilot in this dataset was around 30, which is already quite high. So this makes it very challenging to use the transverse mass with the neutrino because your entire event is spoiled by pileup and you cannot directly reconstruct easily the neutrino. So the transverse mass is very difficult to use. So what we basically do is we really focus on the muon only, and we check or we control the muon kinematics, and we try to extract the double mass from that only. So if you want to do that, we need to have a very precise calibration of the muon momentum scale. That's the first ingredient. And also in our case, we don't use electrons because we have a very heavy tracker, and the electrons related to branch Shalom, and this leads to suboptimal reconstruction of the electrons, so we only focus on the muons. The next challenge is theoretical modeling. I will talk about that later today, but the baseline is that we use state-of-the-art theory inputs as a starting point, and then we use in situ constrained data to get the theory right. And then also very important here is that we want to measure the W mass, but we also have the Z mass or the Z data that we can use as checks. So we use the Z data as much as possible for independent cross checks, which is opposed to Atlas and CDF. They use the data of the Z to calibrate their theory modeling and to calibrate their experimental uncertainties. So we don't do that. We use the Z as independent. Okay, so this is CMS. I think the majority of people know how it looks like. For us, for the double bottom mass, what's important is the tracker here, and then the muon system that is used to identify the muons. So basically, we only use those elements on the CMS detector to measure the mass of the W. This is one of these events taken in 2016. So yeah, you have here the interaction point. You have this fate line, which is the very high energetic muon, which you need to precisely reconstruct. You have some hadronic activity due to pilot and recoil of the W, and then here you have this neutrino, which is not protected because it escapes the detection. So how we go forward more practically? So we have this single muon event selection. So basically you have some basic trigger criteria, etc. And we select the muons in the range of 26 to 56 GeV, which is enough to measure the Boltzmann mass. And we also restrain the muon to eta 2.4, which is basically the acceptance of our CMS tracker. So then what we do is we extract the W Boltzmann mass in a phase space, in a three-dimensional phase space, which is the lepton pseudo-rapidity, the lepton momentum, and the charge. So if this is a three-dimensional phase space, so for both charges of the W, and the reason why we do that is that why we add this pseudo-rapidity, because it's very sensitive to the PDFs, and the PDFs are very important ingredient and a very important impact on the W mass. So that's the reason why we use the eta here, because you can constrain the PDFs. I will talk about that later as well. So if you for a given charge, this is for the W plus, for example. So if you want to visualize the eta and the PT plane in the 2D here, you can see here the unrolled distribution. So here you see overall the lepton PT, and in each bin, this is the pseudo rapidity of that bin. So this is all these points contributed to this phase space, and also for the minus of the W minus. And in total, you have around 3,000 bins that you use to extract the mass. So what we do with the Z? So I said before that we use the Z only as cross checks and validation. We don't use directly the Z to calibrate our theory or to calibrate our experimental certainties. So we have a Z selection to do some cross checks, and we also have W-like selection where you basically you reconstruct your set, but you remove one muon, and then you have kind of a W-like configuration if you treat one of these muons as the neutrino. So this is basically what we do, and then you can also construct this two-dimensional unrolled distribution for the Z, and it looks like this. So it's quite similar to the event selection. So we can test our theory approach, our experimental approach, and then we can see if that makes sense, and then we can use that the same for the WMS. The first ingredient for the analysis is muon efficiency. I only have one slide on that. It's a hard thing to do, but I only have one slide. So the efficiency is very important because you need to compute your efficiency between Delta Monte Carlo in the lepton PT. So you need to have a very granular way of doing the efficiencies to understand every detail of your reconstructions, the tracking, recall, identification of your muon trigger and isolation. So this is basically computing here. So these were done on the Z because there is no other way, there is no other source of information here to do that. And then we do that in a very granular way as well in the lepton PT in the eta charge to control all the efficiencies. The next very important element in the analysis is the muon momentum scale. So basically, so we want to measure as precisely as possible the muon momentum, which is basically based on the curvature, which is 1 over PT of the track. So as I said before, we have we select our muons in the 26-56 GeV range, and in this region, the measurement of the PT is dominated by the image tracker because we have a very straight line here, and the muon system does not contribute too much. So we only use the muon system here for identification, triggering of muons. So in order to calibrate your muon momentum scale, you need to do that to the 10 to the -4 level. Basically, because any change in muon PT is directly proportional to a change in W mass. So if you don't calibrate well your muon momentum, you directly see a bias in your W mass. So that's the reason why we need to control that to 10 to the -4 level. So what we need to do to control the PT of the muons, basically we need to understand the magnetic field, the detector material, and also the interaction, and also the alignment of your detector. All these expressions or all these elements in this for this calibration, you can summarize them in this canonical formula, which is basically the track curvature, the delta of the track curvature over the curvature, is basically this formula, which takes into account all these terms in terms of magnetic field, material, and alignment. We then use, so the way we extract these parameters is based on James I will talk about that later, and we use the Z and also the epsilon to validate this approach. So how we start with the muon momentum scale calibration, so basically it's based on 4 stages. So we take our standard CMS tracks and CMS reconstruction of our events, but before doing that, we remove already some small biases by increasing numerical precision in GEANT4. This makes things much slower, but in the end, this is what we need. Second part is the track refit. So we take the tracks from CMS reconstructions, from the default reconstruction, but we refit them with the new approach with the continuous variable helix in order to remove biases, improve the magnetic field of the detector, and also the material modeling. So that's included in this CVH. Then the third step on top of this is to remove local biases. Local biases meaning biases that you can introduce at pixel level, at module level of your detector. So this is the third step, and then the fourth step is to finally calibrate the residual differences between Delta and Monte Carlo using the James I. So the evolution of these steps, of the first 3 steps, is what you see here on these plots. So on the x-axis is the charge times PT of the muon. So this is the plus muon, this is the minus muon. And on the y-axis is the scale, relative scale, 10 to the -4 level. So this is what we have if we use CMS tracks. So by default, and you can see here that the scale is very large, and you will induce 800 MeV uncertainty on the W mass. So that's what we have in CMS. So clearly that's not what we want. We need to do better. So then we use the CVH track. You improve it with a factor of 2, so the bias becomes 400 MeV. And then if you remove this third step, if you remove the local bias, you go down to 8 MeV. Clearly, that's not yet enough, because if you want to measure W mass up to 8 MeV or 10 MeV each, we need to reduce this still with a factor of 10. And this comes then with this formula. So any residual differences in the muon momentum scale, we can absorb with this formula. So this is this canonical formula that takes into account all these 3 elements that can affect the muon momentum scale. And we use them, we use the James I to mu, so very low resonance mass distribution fits to extract the parameters A, epsilon, and M. And you can see here how these parameters look like for the as function of the muon muon eta for the 3 different parameters. You can clearly see here that there is structure in the B field, in the energy loss, and the alignment. You can clearly see some oscillations basically to remove any bias here. So how do we validate this? How do we know that this approach works and that these parameters are correct and correctly estimated? So we can check the closure of these parameters on the Z and also the epsilon. So basically, this is what we do here. So this is a kind of complicated plot, but basically this is the scale that you extract, or the curvature bias that you extract. If you extract the parameters either on the shape side in green, which is a self-closure, then if you extract the same parameters for the Z to mu, so you can see here the blue points here, and then for the epsilon in the central region here. And all these points, they fall nicely within the statistical uncertainties, which is shown here on the bands. So clearly, this is a good validation of this new momentum scale calibration. So in terms of uncertainties related to this calibration, what we basically did is we took the statistical uncertainties of all these fits, but we kind of inflated them a bit with a factor of 2.1 in order to cover for potential biases that we found, small biases, of course, that we found by doing different variations of this calibration. And we found that if we inflate by a factor of 2.1, you cover most of these biases. The other uncertainty that we have is based on the Z closure. So we calibrate, I mean, if you look at the numbers here at the Z, so we assume that the lateral Z data is correct, and then we see that I mean, based on these inflations as well, we have here the Z uncertainty that takes into account also this for this uncertainty. We also have additional resolution uncertainties and corrections, but they don't matter too much. The baseline here is that how we finally validate our real momentum scale is try to measure the Z mass and see that it comes right. So we did that with our calibration, and then we extracted the Z mass and minus the PDG mass that we assume is the true one, basically from lab, and then we have a minus 2.2 bias with an uncertainty of 4.8 MeV. So this is perfect in line with the set PDG mass. And the uncertainty is 4.8 MeV, so this basically means that we could calibrate our neurons to a 5 MeV level, which is pretty impressive. So basically, this proves that we can control this momentum scale to the 5 MeV level. People say, can we interpret this as a Z mass measurement? At the moment, no, because we used the Z mass uncertainty as uncertainty in our model, so we cannot claim this is a Z mass measurement. We will work towards it in the future. But at the moment, these are just validation numbers for our WMS. Then the next big chunk of the analysis are the theoretical challenges, the theoretical uncertainties. Basically, you can, based on the way we produce the Ws and indicate the Ws, you can categorize them in the PDFs, QCD, electroweak, and QED. Electroweak QED is not that important in our analysis. I will not spend too much time on it, not at all. But the most important part is the PDFs and the QCD. For the PDFs are very important because it depends on the polarization of the W, and it also affects the kinematics of the lepton. So clearly we need to understand the PDFs. And this is one of the dominant uncertainties in the analysis. And then for the QCD, this is also a very important aspect in the analysis. Because if the W in W in the event is not produced at rest, there is always some boost of some PT spectrum due to gluon emission or gluon radiation of the colliding quarks, which is basically shown here. And this is very difficult or very hard to calculate precisely up to the level that we need. If you look at the Z, for example, which we can use to check, we don't use it to control, but we can use it to check. If you look at the ZPT and with our best estimate and state-of-the-art uncertainties, this is the result that we have, ZPT. So this is data Monte Carlo, and you see already a 10% difference, 10% discrepancy. And this is with the best knowledge that we have, theoretical knowledge that we have. So clearly we need to improve this by having in situ constraints in order to have a better description of the theory modeling, especially here, where we have a lot of data in the low PT region. So how we did that? So the approach in general is to to construct uncertainties, different uncertainties for different regions of the kinematic phase space, and try to constrain these uncertainties in theory. So that's basically what we wanted to do, because we have a lot of data, so we have constraining power to do that. So we started from a huge sample, 4 billion events, which is based on mean law plus PTI and photos, which is next to leading order accurate in alpha S, but has a limited accuracy has a limited logarithmic accuracy. So in order to improve this last point here is that we apply corrections on top of it, resummation correction based on setlit, and we match them with dy turbo to fixed order predictions. So basically, our sample then is n cubed LL plus NLL accurate, which is more or less state of the art, the best what we can have at the moment. And then based on this is the baseline that we start with. We then construct a robust uncertainty model for all the possible effects that we still miss in order to understand these reasonable differences. So at low PTV, at low W or Z boson, we have non-perturbative effects. So basically, this is due to the small motion of the partons in the PDF. So we assume that the partons always go straight with the beamline, but there's always a little motion transverse direction. So ideally, they have this TMD, transverse motion dependent PDF, but these are quite complicated objects to deal with. So we have a more empirical model where we smear the transverse component of the parton with some Gaussian firm in order to take into account the non-perturbative effect. And you see here for the ZPT, you see here clearly that the non-perturbative effects, they play a role massively at very low PT of the W or the Z, and they don't play a role at higher momentum here. But the uncertainties here are quite large, basically because we don't know, because it's an empirical model and we don't know what are the initial values, basically. So we take a very conservative initial parameter, and then we are data constrained. Then for the intermediate PTV, so there we have this novel concept called theory nuisance parameters. So basically, this follows naturally from the result calculation. So this is from the setlib package. So what they do there, this is from the theory community, of course. This is something that we developed, but we used it in our measurement. So we started from this n-cubed sample that we have. And then what the theorists did is they based on the resummation orders in the calculation, you can assign terms that you can use them as uncertainties in your fit. So basically, what you have here is the PT of the W, and according to the different terms in this different calculation, you can have different shapes here. And by combining them all in the fit, you can have a nice constraining power to measure to control these uncertainties. So this is for the PTW, how that translates then in the PT mu, which is basically the spectrum that we measure. So this translates here. So the majority, the big ballpark here is around 40 MeV, which is the Jacobian peak of your spectrum. So by having all these uncertainties, we can nicely constrain them in the data. Then PDFs. So there are many PDFs available, and we tried some of them. Basically, you see here in the table CT18, CT18Z, PDF for LHC, MH8T ones, and then also the NNPDFs. So we tried all these PDFs, and we wanted to understand how they relate to each other. Because they all have their own fits, they all use their own data to construct them, and we want to understand what are the reasonable differences. So what we did basically, we tried all of these PDF sets and tried to measure W amounts with it, and we wanted to see how much they differ from each other. So you take one PDF set and then you try to fit it to the other one and see what is the difference in the W amounts. This is based on Monte Carlo only. There's nothing to do with data here. And what we found basically that all the PDFs that they are not very consistent with each other, which can be understood to some extent. We don't care too much about it. What we did in our approach is to inflate the prior of the PDF such that the overlap matches. So you see here the scaling factor that you need. So for this CT18Z and CT18 PDF LG, you don't need scaling factor. You can just take the uncertainties as is, but you need larger uncertainties for MH80, 20, and NMPDF, and especially for NMPDF, you need a large scaling factor because there are very small uncertainties, pre-fit uncertainties. So in order to cover for all the rest, you need to inflate it with a factor of 5. We chose at the end the CT18Z as the nominal PDF set, basically because we don't need scaling factor. It gives you a good impact on the results. One word about angular dependency on W and Z production. So this is the last piece of the theory. So you have these angular coefficients. Basically, they come from the angular decomposition of the W production, W decay. So you have the unpolarized cross section, and then you have the angular decomposition here, which is this typical 1 plus cosine squared theta term, and then you have all the rest. So these AI terms here, they are predicted by mean law, so by our Monte Carlo generator. And basically, the uncertainties on this AI, we just value the scales here up and down to have some uncertainty and some degree of freedom here for the AIs to be controlled. So this was all the ingredients necessary for the theory. So how then we validate this theory modeling? This is a very important aspect because we rely on a lot of constraining power on the data. We rely on a lot of inputs from the theory, but the question is how can we trust all these procedures? And so we need the thorough validation of this theory model. So this is shown in this slide. So we have 3 ways to validate our theory. First, in our uncertainty model. So the first is you use the Z data and you directly fit the PT of the time system. So this is shown here. So you have the Z, you can perfectly reconstruct the Z PT because you have the 2 muons. And then you fit with the theory model that we have, we fit them, and you basically can see here, this is now the post-fit uncertainty. But it seems, or this proves that the degree of freedom we introduced by the theory modeling can completely absorb. The second important validation is the W-like, what I mentioned before, by removing one of the muons in the Z event selection. So this is similar to the W boson mass, but now we want to extract the Z mass, basically by measuring it from the PTL from the muon. So this is what you show here. This is also post-fit. And you can see here, if we do the Z mass extraction based on this W-like analysis, you have a -6 bias, plus or minus 14 MeV. So this is a very good result. And this also proves that we can measure, that we can control or we can trust this theory modeling that we have. The third part is by comparing both. So by comparing 1 with 2. So what we can do is we can check the unfolded spectra of 1 with 2. So this is shown on the third plot here. So you see here these 2 bands, which is the unfolded spectra of your PTW, of your PTZ. And here in blue is the direct PT mu fit. Basically, it's a unfolded spectrum of this one. And this is the W-like fit, so the unfolded value from this fit. And you can clearly see here that the overlap is very much or almost perfect. So this means that you can extract, or we believe that we can extract, or we can control the theory uncertainties by doing this W-like fit. And this then gives us good confidence that we can do the same with the W mass. So this is the final validation of the theory that we have. So before measuring the W mass, there are a few other ingredients that I want to mention on this slide. So that, as I said before, the transverse mass we don't use as an observable to extract the W mass, but we use the transverse mass as a cut for non-prompt, because we also have a non-negligible non-prompt background based from V to mu decays. So we use this transverse mass to place the cut. And then for the non-prompt background, we have a sophisticated data-driven approach, which is basically an extended ABCD method, which is shown here. It's not the ABCD, but it's like in a few more other regions in order to control the correlations. And basically, this is what we have here, and we can pretty much control this non-prompt background as well using this extended method. So then we moved on to the final fit of the W mass. So all the ingredients were in place, and then we unblinded the result, and you have a nice 8360.2 plus or minus 9.9 MeV, which is very close to the CDF sensitivity. So this is spot on with the standard model, as you can see here. I mean, close to spot on, let's say. And this is, of course, yes, the most precise measurement of the LHC and in clear tension with CDF, which is still left alone here on the right side of this plot. So clearly, yes, this is our result here with very nice uncertainty comparable to CDF. So we are very happy, of course, with that result. If you look at the uncertainty breakdown, so yes, the mu momentum scale, this is of course the same as for the Z mass, so this is pinned down to 4.8 MeV. Then we have from the theory, we have the angular coefficients with the 3.3 MeV and then the PTV modeling. And you also see here the PDFs, despite of having a strong constraining power, it's still dominant with the 4.4 MeV uncertainty. So this is the more or less the breakdown of the analysis. Only also interesting to notice is that the data sample size is only 2.4. So the impact on W mass is, I mean, for the statistics point of view, only 2.4. Because we use already a very large data set. This is the result that we have for the 2.4. We did some extra checks, experimental checks, theory checks. So the first thing we did is we checked the W mass in different regions of the detectors to see that we don't have any bias based on where we look at. So this is the difference in W mass by extracting it in different bins of pseudo-activity of the lepton. And this is, of course, the uncertainties are larger because now you have less statistics, but basically you see here that everything is within uncertainty is consistent with the zero line. More interestingly here is what we also did is the charge difference. So we wanted to measure the W plus minus and W minus, which we assume should be zero because they should have the same number, numerical number. And what we found here is that we have a 57 plus or minus 30 MeV uncertainty. This is almost 2 sigma. So this is not yet worrisome, but it's interesting. So of course we did a lot of checks to understand this, and what we found is that by doing the charge difference fit, we found that it's highly correlated to up to 40% with the alignment terms of the calibration. And there is also a high correlation with some of the angular coefficients related to the W polarization. Basically, they play in a similar way. But what we found is, okay, we have this result, but what we found is that the final impact on the W mass by potentially missing one of these uncertainties is very small. So we estimated it to be less than 0.1%, 1 per MeV. So we are not worried about this because in the end, what we do, we measure one number, one W mass. We are not sensitive. We don't want to measure the charge difference. So if we wanted to measure the charge difference, our uncertainties might be a bit different. So we don't consider this as very worrisome. Then some extra validation checks regarding theory and modeling. So we have our baseline theory modeling with the uncertainties. So we also tried different models. We tried different estimation schemes, so different theory news and priors. We also tried by reweighting the PTW using the PTZ. So this is done by Atlas to some extent in their W mass measurement. So this we also tried that. And we can also do a combined fit of PTW of the W mass with the PT mu of the Z to see where the correlation is. And now for all these things that we tried, we can basically see here that the results are quite consistent with each other. So basically, the W mass is, I mean, we can measure W mass with all these ingredients and basically it's all pretty stable. The last thing we checked is the PDFs. So as I mentioned here, we have the scaling factors. So this was also interesting to see if we don't apply the scaling factors, what will happen. So here is and also what we have if we apply with different PDF sets. So this is the result that we have if we have with scaling. So everything is nicely consistent with each other, regardless of the PDF set we use. So this is something that we wanted. That's the reason why we have the scaling factor. So if we also align W mass without the scaling factor, the results are not dramatically worse, but you see here that the scatter or the spread is much larger, and they start to become at boundary level here. So basically, this means that this proves that the scaling factors we applied here makes sense to put everything more or less in line with each other. So yeah, this is the interpretation later we fit. Don't spend too much time on that. These are just propaganda plots. But I want to go to the conclusion directly is that yes, so CMS delivered the first W bottom mass measurements since a long time, so a few years of trying to measure this. So we use here a very large data set with innovative theoretical modeling and you see the constraints. And we have a very good and very nice momentum scale down to 5 MeV, which in the end we also want to use to measure the Z mass. And then the conclusion for WMAS is that we have this number with the 9.9 MeV uncertainty, which is in a standard model here and clear tension with CDF. So I think the picture is standard model-like. And then we have to interpret this CDF in a different way and see how serious we need to take into account at this point. I have one slide still. What is next? So yes, we are not satisfied. Of course, we want to do more. So we want to use the next runs of LHC or the next opportunities to measure WMAS. So the weakest point of the analysis that we have now is that we only look at the muon kinematics. We also want to look at this transverse mass distribution to have an independent cross-check as well. So we want to use low pilot data that we want to take next year or in 2026 in order to validate this transverse mass techniques in a hadron collider environment, which is very challenging. So that's basically on the table. We want to do the Z mass measurement. And we want to do many things in order to improve this analysis and to further pin down the WMAS certainty. Okay, that's it from my side. Thank you for your attention.
Thank you, Dr. Jan. So if there's any question, please go ahead.
I would like to know your opinion about the CDF result.
Yeah.
So is it a wrong result? Is it a new analysis necessary? Or?
Well, I read it from CDF, so I don't know. I know that when they published the result, there were 2 years of discussion, try to understand them. And for them, it took them 10 years to get to this result as well. So it's not, they didn't do stupid work, let's say. It's 10 years of hard work to get to this result and it's uncertainty. But to fully understand this, that's very difficult. Maybe we will never know that. And it can, what we think or what people think is that it's an unfortunate combination of few effects like momentum scale, some bias, and some bias in the theory modeling that they have, which then could move to this offset. But to fully understand this point, I don't think we will ever know it because they will not reanalyze the data. They will not go deeper anymore because you can go infinite, of course. And it seems that all the other experiments and also standard model are quite aligned with each other. So yeah.
Different question. At the beginning of your talk, you mentioned something about the polarization of the W boson, right?
Yes.
But I understand that you say that you obtain the different polarizations when you see the angular distribution of the muons, right? Or how do you obtain polarizations?
Well, we're not directly sensitive to polarization. It's more through the uncertainty model the theory uncertainty model that we have that we introduce sensitivity to different polarizations. This mainly comes from the PDFs. So we have the charge difference, of course, which is a big thing, and then we have other directions and theory dimensions where we have sensitivity to polarization, but it's due to the theory uncertainty model that we have that we are a bit sensitive to the polarization. But we don't directly measure it.
Is it possible?
To directly measure the polarization? The polarization itself, no. I mean, I need to think about that, but that's a challenging thing to measure. You can measure the helicities of the W. This is possible, and this, in fact, I didn't mention it, but we also did an additional which is the realistic cross-section fit. So it is related to the polarization of W, where we extract the W mass based on these angular coefficients. Because all the angular coefficients also depend on the mass. So if you try to measure the angular coefficients, which is very sensitive to polarization, etc., you can also infer the W mass. So this is an additional fit we did in order to be less theory dependent.
Great.
Yeah.
Thank you.
You need more. You need more granularity for that. So you need more data for that. Yeah.
Anybody else?
About the mass difference between the W bosons, well, the mass of the
Yeah.
boson.
This one.
Yes, for me is that, well, I have two questions. The first question is about that. If you expect that mass difference be less, this is your result, and maybe in the future.
Yes. So the first thing about this difference is, yeah, so first we expect it will be zero. I mean, we expect that W plus and W minus in the same mass. So this should be zero. The reason why we see a 2 sigma deviation here is it's very likely that in the uncertainty model that we have, we don't have enough we have too strong correlation of the charges, because we have a lot of uncertainties, experimental uncertainties, and theory uncertainties that are charge correlated. And it seems that there is too much tension in the fit to absorb this charge correlation. So we did a lot of checks by decorrelating some of the uncertainties with charge, and then we could understand this number. So this is basically a shortcoming of our uncertainty model, or likely from our uncertainty model. The reason why we don't care is because we explicitly prove that the impact on the W mass itself is zero. If we want to measure the difference, if we really want to measure the difference, we need to improve our uncertainty model and our correlation model in our fit.
Okay, thanks. The question was because when you study extensions of the standard model, the most simple extensions are the ones that extend the Higgs sector. And extending the Higgs sector may give you different kinds of patterns of electroweak. And in some models, you can have different mass of the W bosons, which are models. Well, that was my question.
You mean there are models with different charges, with the mass difference in charge?
Yes.
Yes, yeah.
Might be.
Yeah, we don't claim this is real. It's only 2 sigma, and yeah, we did a lot of checks, and we saw that the impact is small, and we understand why that is.
Okay, thanks.
I think online we have questions.
Just have a question about the ILOP being low. How do you plan to achieve that for future?
That's a request to LHC. So we need to ask LHC to not collide with full intensity, but collide with less intensity, less bunches, or not head on, but with some offset of the beams.
Fernando, you can hear me?
Yes, I can. Actually,
Okay.
my question is related to this last one. So you are saying like uh, to improve these measurements with more data, you are fixed with log pileup data sets. So the round tree is like for until now it's like not helpful in this way, right?
Yes.
But
No.
so
Go
no,
ahead.
so I want to ask if with this in this plot that you shows the comparison between the mass of the W with the other experiments seems like Atlas has a good statistics. It could be like could be made a mix of data sets with Atlas to make a better uh, measurement.
Well, the combination with Atlas is certainly ongoing now. So